Assalamu alaikum. This is lecture 2 of our machine learning course, and in this lecture I'm going to discuss further about the basic types of machine learning, and particularly the focus will be on the supervised learning. And apart from that, in this lecture we will discuss our first learning algorithm, famously known as naive Bayes. So as I mentioned earlier in this lecture, I am going to further elaborate the concepts of supervised learning which we learned in the previous lecture. There are certain criteria which you have to meet in every model selection in supervised learning. So we will also take into the consideration of those required criterions. And then we will focus toward the actual learning algorithms, and there are different kinds of learning algorithms. So we will discuss about discriminant learning, and there will be discriminant functions and association rule mining techniques. So these are basics of naive Bayesian algorithms, and after this uh, discussion and some problem solutions, we will move over discussion to the actual implementation of naive Bayes classifier. Naive Bayes classifier is actually a combination of probabilistic and deterministic models. So in the discussion of naive Bayes classifier, we will discuss the relevant issues that the naive Bayes algorithm suffers from. And finally, we will conclude our discussion to cater the continuous variables or continuous attributes in the data by examining Gaussian functions. So by now, from the understanding of previous lecture, we have come to know that learning a class from example is one of a specific type of machine learning task. For example, you want to identify a particular class, a data set, or a data vector belongs to. For example, in this case, we have a class C, which is an arbitrary class which can be assigned any uh, expected target value. So for example, in this case, we have a prediction function and a knowledge extraction function from the data. So our goal is to predict the class of the cars based on some input feature attribute. So if we have a set of data, we actually want to predict the type of the car as an outcome. So in the prediction, we stated that is the car X, which is the feature vector, or the input value is a family car. So if the output of the function is true, we will say that it is a family car, and if the uh, prediction is false, we will say it is not a family car. Again, how will you encounter or how will you reach at this decision, which will help you to classify that on what basis you will say that the specific example is a family car. So this is the knowledge extraction. So in the knowledge extraction, you or your algorithm will need to know what type of input data is required to typically classify a car into a family car. So in this particular example, we will say what do people expect from the family car. More generically, in terms of machine learning, what types of attribute will make a car as a family car. So once your function predicts the output, it may have the possibility to predict a positive clause or a negative clause. So in this case, positive clause will mean that if you have a particular input example and your algorithm correctly classifies that example as a family car or not a family car, that will be a positive example. On the other hand, if it does not uh, classify as a family car, it will be a negative example. So for this particular example, we have a feature vector with two attributes. The first attribute is referred as x1, which is price, and the second attribute is referred as x2, which is the engine power. So from now we must have the understanding about the dataset and the two subsets of the datasets famously known as training set and the test set. So whenever you want to make the prediction or extract the knowledge, you first have to train your algorithm on the training set. So there are several conventions to mark a training set. For example, in the previous lecture, we defined the term for the dataset as an instance space. So similarly, if you have the instance space, you can divide this instance space into multiple divisions so that you can have different sets, for example, training sets, test sets, and the validation sets. So we use a notation as a capital letter X to denote the training sets. So similarly, the small letter x uh, will exemplify one particular case or in one row in the dataset, or in the machine learning term, one example or one feature vector. So the training set consists of input attributes referred as x and the output target values or the resultant values referred as r. So t from 1 to n specifies that it implies from the example 1 to number of examples present in the training set. So again, conventions are different for different writers. In this case, we have the output examples as marked as or. In some cases, we have output examples marked as small letter y. And if you want to assign all the output attributes or all the target values, you can use the capital letter Y. So if you take the example of the previous lecture, in the case of Johnny liking the pie, we had number of attributes such as filling size, crust size, thickness, etc. These were referred as input attributes, and the output or target values were referred as R, which were positive or negative examples. Positive stands for Johnny likes the pie, and the negative implies that the Johnny does not like that particular type of pie. So again, these are referred as R and Y. So if our input example is uh, calculated as the result of a positive attribute, or in this word the result is equal to 1, we say that x belongs from the positive class. On the other hand, if the resultant value is 0 or negative, we say that the input example is from the negative class. So this is another form of specifying input features in the form of matrix, and when we take the transpose of the matrix, you will have the vector attribute form. So as you can see, uh, we have dummy data represented here in the graph, which represents different values, and on the axis we have, on the x-axis, the first attribute price, and on the y-axis we have the second attribute engine power. So there were numerous examples, and some of those are classified as negative, which are marked in the red circles, and some are marked as the positive, which are marked in the purple circles. So based on that data, we want to extract a rule that will predict of the values of these training sets. So if you carefully look at the graph, you will understand that the positive examples are lying in this area for the first attribute. So you took the first attribute and you say that if the price lies in this region, there is the possibility that the examples will be positive. So as you can see, there are negative examples as well. So you have to complement it, or add it with the another attribute, which is our second attribute, and we have also specified a partition here which says that if the engine power is greater than E1 and less than E2, this will specify the positive example. So in our case, this is the area where the positive examples lie. So any of the next uh, examples which will be fed to this classifier will be predicted on this function. So if the prediction is positive, it will be marked as a positive class, or it will be marked as V1. So on the other hand, if prediction is 0, it will be marked as a negative class. So it is essential to understand here that whatever assumption you have made here, it is particularly dependent on this data. So for the same example, if you change the data, for example, if you have another type of data where the positive classes are also here, you have to change your assumption and you have to retrain your classifier to correctly predict the upcoming example. Otherwise, your assumptions will be failed and you will not have better accuracy on your classifier. So this leads us to the definition of hypotheses or assumptions inside our algorithm. So we can have number of assumptions. For example, we must have used this assumption, or the assumptions provided in the yellow circle or in the blue circle as well. So there can be many assumptions or hypotheses that will prove our data to be lying on the positive and negative examples, or in other words, that is useful for our data to classify the examples correctly. So you have to keep in mind that there are more than one possibilities, or there are more than one solution to your data, and each of the solution or the solution set is represented as the hypothesis set, referred as the capital letter H, and any of the hypotheses you take is a kind of function that translates the input examples to the target labels based on those assumptions. So your assumption again may lead to 1 if your hypothesis says that the particular example X is positive, and it can lead to 0 if your hypothesis says that this example is the negative example. So if your algorithm misclassifies, for example, if your algorithm classifies a positive example as a negative example, this will mean that your classifier or your hypothesis is making errors. So you can calculate errors by counting the false positives or false negatives. False positives are the examples which are marked as positive, but in the real case they were the negative examples. For example, a business car is marked as a family car is the typical example of a false positive. On the other hand, false negative is the incorrect classification, which means a family car is marked as a business car, for example. So the error rate is measured again by the capital letter E, and it is measured on the assumption or hypothesis over the training set. So for each example, you will calculate the assumptions or hypothesis function on the training set and compare it with the target attribute. So if your hypothesis assumption of the example or your calculation of the example does not equals to the resultant value or the target attribute, you will count these values as errors. So if these values are equal, you will ignore the values, which means there is no error. So for example, if we have taken this assumption for the positive clause of the engine power, we may have the hypothesis in this form. So we may get some negative examples in our hypothesis. Therefore, these are termed as false positives. So again, it is critical to find out the correct assumptions about the data to make the accurate prediction. So you can use various kind of measures to find out the assumptions. So you can have multiple hypotheses. For example, you can have a more specific hypothesis and a more general hypothesis referred as S and G. The more specific hypothesis will contain the conditions where only positive examples are classified. So, on the other hand, most general hypothesis is the possible condition or possible hypothesis in which the positive examples can occur. So between that there is a classifier which correctly classifies the positive examples, maintaining a difference or distance between the specific examples or specific hypothesis and the generic hypothesis. So this hypothesis is between the specific and the generic hypothesis and is consistent with both of these and make up the whole Woolian space. So you have to choose a hypothesis with the largest margin. That means the margin between the positive examples and the negative examples should be large enough. So as in this case, you have chosen a, a hypothesis which has the largest margin between the generic hypothesis and specific hypothesis. So if you have chosen, for example, this hypothesis, there is a very minute gap between the positive and the negative examples. There is more chance that your algorithm will less likely to succeed in this environment and more likely to predict the wrong classes. This leads us to the discussion of another important concept called VC dimensions. So whenever you are representing the examples or points in the classifier or in the output mm, plane, there are n number of points which are the total number of examples. So these examples can be labeled in 2 raised to power n ways as the positive or the negative example. So if you take the simple consideration that if you have only two examples, you can have the representation of positive and negative examples in the four ways. For example, taking this case, we have plus plus, positive positive, positive negative, negative positive, and negative negative uh, scenarios. So for these cases, your hypothesis has to shatter the input space or input examples if there exists an hypothesis which is consistent for any of these VC dimensions. So uh, let's explore it more with the help of an example. So the VC dimension states that if any given classifier separates the positive and the negative example, no matter how the labels have been assigned, we can say the classifier shatters the set. For example, if you have the previous example and your algorithm correctly classified the example, you can say your algorithm has the VC dimension of some number and it separates these examples, or in other words, it shatters the set. For instance, if you consider this example, a linear classifier shatters the following three examples in two-dimensional space. So you can use different classifiers or different hypotheses to shatter these three uh, attributes or three examples. So you can use this algorithm or this classifier. It will separate the examples from 1 with the 2, or you can use this. Again, it will result in the same, or you can use the third one, which will also result in the same division, and on the fourth one, it will classify all three examples into positive or negative, and there is no example on the other end. So VC dimension in this case is the size of largest set of examples shattered by the given classifier class. So VC dimension states that how many examples you have shattered by employing a classifier. So if you take this example, you have three attributes and your classifier can correctly classify or shatter these examples. You will say that you have the VC dimension of your classifier equal to 3. So again, 3 points in the two-dimensional space. For another example, if we have, let me draw another example in which we have three attributes or three output examples in the same line. So we may not use a classifier that can classify these three examples horizontally in one line. So we have to use a different classifier such as a polynomial classifier to classify the examples using different classifiers. So this leads us to the discussion that what kind of hypothesis or assumption you should make. What should be the basic criteria to select the hypothesis or select the classifier. For example, in the graph illustrated here, we have two hypotheses. One is marked as H1 in the rectangle bracket, and the other one is marked as uh, ellipsoidal shape in the H2. So which kind of hypothesis is more better to choose? So as you can see, in the H1 we have one error. However, in the H2 there is no error and the algorithm correctly classifies the examples. So if we have not explored the model complexity, we will clearly see that hypothesis 2 is the best and suitable choice instead of hypothesis 1. However, these are not our target goals every time. For example, we may use a simpler model which will be easy to use. In other words, it will be easy to calculate the examples, or in mathematical term, it will have lower computational complexity. So for example, in this case, it is very difficult to find or differentiate these kind of examples using a circular or an ellipsoidal shape. Therefore, if our target does not require the extreme accuracy, we may prefer to use hypothesis 1, which is easy to use or simple to use and have low computational complexity, instead of the hypothesis 2, which is more accurate but it may have higher computational complexity. Secondly, you may also want to have a model which is easier to train. That means it requires very least amount of space. And in some cases, uh, when you have to explain the results of your classifier to the people, you would like to have the hypothesis which is easier to explain instead of the most accurate hypothesis. And also the end goal is the generalization, and the hypothesis which generalize better or have the low variance to perform better on the unseen training set or test set, which will be chosen from the candidate classifiers. So uh, whenever you come across these kind of decisions, always have this checklist in your mind, that what kind of classifier or hypothesis you will prefer to select. So the checklist is simple. You have the simplicity in the computational complexity, in the space complexity, and sometimes if you need the explanation of the desired targets, you will like to have the model or hypothesis which is easier to explain. So far we have discussed about the cases where we only deal with the two-class problems or the binary classification or similar examples. For example, in the examples we have discussed, there are only two possibilities. For example, we have positive output target and a negative output target. However, most of the cases in the machine learning may not have the binary classification, and there can be more than two classes. So this leads us to the multiple class or multiple classification models. So the classification are marked again with the symbol C, but this time we have more than one classification ranging from 1 to K. So in the same case, we have the training set marked as the capital letter X, and we have the feature vectors and the target attributes for each of the examples. However, now we have to calculate the probabilities of the examples for each type of the class or each target label. So our target label will be indexed with the R of I, or in other convention Y of I. So it will be 1 if our training examples belong from the stat specific class, and it will be 0 if the examples belong from some other class which is not equal to the current class we are checking. So for example, if we have the hypothesis to train our dataset on 3 different kinds of cars marked as family car, luxury sedan, and sports car. So our input attribute will be marked as same. However, we will check for result of family car, result of luxury sedan, and result of sports car, and if our calculation results in 1 for any of the calculations, we will say that this example belongs from that particular class, and if it results for 0, it will belong from some other class. So again, you have to train multiple hypotheses for each class. That means for each class you have to train a binary classifier, or for each class you have to have a binary hypothesis, so which will result in positive class for that particular class in the examples. So again, the hypothesis will have index based results for each type of output label or each type of clause, and it will be 1 if it belongs from that clause and 0 if it does not belong from that class or some other class. So for example, we may encounter this example and we calculate the resultant values using the set of hypotheses. And first, our hypothesis in the first case, for example, in the hypothesis of family, we will result in 1. Therefore, this will be marked as the family car, and for the rest of the hypotheses, for example, hypothesis of the luxury, it will be 0, and hypothesis of the sports, it will be 0. However, there are some uh, more problems in the multi-class classifications than just identifying number of class. Again, just like the binary classification, you may have some overlapping between, just like in the previous example, you had overlapping between positive examples and then negative examples. But in multi-class problems, you also have the problem of overlapping two classes. So for example, if you have some examples represented here, how will you classify these examples? Either these will be marked as sports cars or luxury sedans, and what will happen, whether you will accept these examples or reject these examples. So there is another problem which represents some kind of anomaly or noise. For example, some examples here may be represented as an unknown class or a new class. So now we have this solid understanding of the classification. That means we have to predict positive or negative examples in case of binary classification, and probable class label if we have multiple classification or multi-class problem. So as with the previous example, if you consider the binary classification, we predicted the output as positive or negative in words of 1 or 0. again we predicted the multi-class problem. If you consider the previous problem in the family car, in the sedan, sports car, and luxury sedan. So again, these were marked as individually binary classified for each of the subclass, and the result was again 1 or 0 for the particular class label. And the class which will have the higher probability will be marked as the output label. On the other hand, in the regression problems, you do not have to mark example as specific type or label. You have to predict the actual value for that uh, example. So regression is more like predicting the value of your car or the value of any other property you want to sell based on the parameters provided as input. So the concepts are similar except that you have to predict the actual value instead of a typical class label. So the training examples are again referred as label X, and we have the training set, input feature, and the output value result marked as R. So just one differentiation here that these represent the actual values instead of the labels. So these are from the large set of real number values for many examples such as prediction of numerical values. So this is value is based on some function which is applied on the input feature vector plus an epsilon value, which is the minimum possible fluctuation or error in the estimation. So we have another example here which predicts the value of our vehicle based on two parameters, the mileage and the price. So based on the mileage, our regression algorithm is predicting a value for the car. So you can see again we have different uh, assumptions or hypotheses, and we have a linear or simple hypothesis and a non-linear hypothesis or a polynomial hypothesis. So the first function is the simple, which calculates a weight, and it multiplies with the input feature x and adds another weight 0 to calculate the output value. On the other hand, if your data is complex, you can use the second order or third order polynomials to calculate the complex values. So as you can see, our simple linear algorithm is the straight line. On the other hand, our polynomial algorithm has the curves in the data set. So again, to measure the accuracy of your algorithm, you have to find out the errors. So if you recall, in the classification, error was the difference between the actual label and the label predicted by your hypothesis. So again, here you have to calculate the difference, and uh, the error is calculated on the function or the hypothesis, which is referred as V here on the training set, and it is the difference of the actual values between the predicted values. So most often these values are squared to uh, to eliminate the negative values so that the errors are calculated as positive values. So for example, if your algorithm predicts a lesser value than the target value, it will be also treated as the error, which is the distance from the positive actual target to the less predicted value. So in more general term, the function you have used, you are calculating the errors on the weights of those functions, and it is again the difference of the target attribute and the predicted attribute. So learning is an ill-posed problem. As you can see, there are so many possibilities that there can be some wrong assumptions while you are choosing the hypothesis. And most of the time, data is not sufficient to find a unique solution. Even if we choose the hypothesis which correctly maps the data to the target attributes, there are chances that your hypothesis will not generalize well. Therefore, you have to make the changes or further assumptions into your hypothesis to cater the unexpected scenarios. So there is a need for an inductive bias, which are again referred as assumptions about the assumption or assumptions about the hypothesis. So we will discuss more about the bias term in the upcoming lectures, that how you have to use these bias to manage or to control the errors produced by your algorithm in the training and testing phase. So this will directly implement on the generalization. That means once you have trained the model and then you feed the testing to your uh, test data to your algorithm, and your algorithm predicts some values, and if it generalizes well, you do not have to worry about the hypothesis. And if on the other hand it does not generalize well, you have to make further assumptions about your hypothesis so that your algorithm adjusts itself to the unseen examples. So there are two common problems with the generalization. One is the overfitting, and the other is the underfitting. Overfitting states that you had a very simple data or a simple classifier, but you have made a very difficult assumption. This uh, can be due to some training or some data noise. For example, if we have a simple data and we may choose a very complex algorithm or complex hypothesis, and when we feed it, this may be because we have some noise in the training data, and the designer is unable to notice that noise and chooses a more complex algorithm or complex hypothesis to classify these examples, and chooses a more complex classifier. And then there are simple examples again in the test set, which will generalize pretty badly and it will overfit the data. Therefore, your model will have the problem of overfitting in generalization. On the other hand, if your hypothesis is less complex, that means you are using a very easy assumption or very less complex assumption to classify the data, your classifier will not be able to observe the patterns in the training or testing or even in the real-time data. So these are two common problems, and To address this problem, there are several techniques, and one of them is the management of bias and variance of your algorithm. The selection of algorithm is dependent on numerous parameters, and three of them are most cardinal to select from. And these are called triple trade-off parameters. And the first one is the complexity of the algorithm. As we have seen that we have to choose the less complex algorithm which have the some predefined level of accuracy. Of course, we do not have to compromise on the accuracy for the simplicity, but in some cases you may want to have some compromise on the accuracy. For example, if we have more complex model which provides 90% accuracy and a less complex model which provides the 88% accuracy, we will likely to choose a less complex model for mere 2% uh, accuracy. We will not want to exhaust our computational devices. Similarly, the another trade-off is the training size. We would like to have a large number of training examples in our training set and the least amount of generalization error on the new data. So again, note that we have to measure the generalization error on the new data, the data that algorithm has not seen before. So as we have more training examples, there is chance that the generalization error will decrease as we have the complex hypothesis. There are chances that the first the generalization error will decrease because our complex assumption has the ability to label examples from different uh, dimensions. Uh, and again, if our uh, assumption is complex than the model, and after some time, our generalization error will increase. Therefore, it is advisable to choose uh, assumption with less complexity as possible. One solution to this problem is to use the cross validation, because most of the time you will not have the available data in the quantity you will like to have. Therefore, to estimate generalization error, we need the data unseen during the training. So again, to calculate the generalization error, use the data that has never been used by the classifier before. So we split the data into three sets: by training set containing 50% of examples, validation set containing 25% of examples, and the test set containing again 25% of the examples. So we can use the cross-validation technique to resample when there is few data. For example, we can divide these sets, and first we choose the first two sets as a training set and test on the third set, and in the second cross validation we can use first and third set for the training and test on the second set. Similarly, we can divide this set and merge it with the other one of the two sets and then test on the third set. So again, in this way you have to train three or more different classifiers. But to calculate the generalization error, you have to have some unseen examples for your testing. So in the conclusion, we will want to have these three dimensions as an output of our supervised learning task. First of all, we'd like to have the model as an output of our machine learning task. The model will be most often is represented as a function, such as in this case g of x over the simple sine theta, and you have optimized this model based on some theta value. Similarly, you will want to have a loss function, which is the error rate calculated on the training set provided by some optimization function. So this is again summation of the difference between the target values and the calculated model prediction. So you would like to have the optimization procedure, such as in this case you would like to have the optimization on the error set, and may choose the optimization which minimizes the loss function. So this concludes our discussion towards the initial part of this lecture. Now we move our focus towards the discussion of our first algorithm or first classifier, which is based on the Bayesian classifier or the Bayesian probabilistic theory. So there are three methods to establish a classifier. First of all, you can make a model rule directly. From the dataset, you can make certain assumptions and make a model for classification rules. So these kinds of models are illustrated further in next few lectures, where we will discuss about the algorithms of nearest neighbor, decision tree, perceptron, or support vector machine. So these models take the consideration of the rules and help to classify examples using the binary classifier. Then there is another possibility which allows us to model the probability of the class membership given the input data. So in this way, you calculate the probability of all the membership classes in the dataset and then predict the output with the most predicted or most higher probability value. So the example algorithms for these kind of classifications are multi-layered perceptrons with the cross entropy cost. So our algorithm in discussion here is from the third category, which makes a probabilistic model of data within each class. So in these models, you calculate the probability of each class and then model these probabilities with the data. And if you have to predict on the new example, you compare the probability with the probability of each class, and whichever gets the highest probability, the upcoming example is marked with that particular class. The examples are naive-based, which will be discussed in this lecture, and other model-based classifiers. So in this scenario, we have three different kinds of classification methods. So the first and the second are examples of discriminative classifications. The third is the example of generative classification, and it is also example of probabilistic classification. So discriminant functions, as the name just discriminate the different type of classification. So for classification problem, and for each class define a function such that we choose any one of the class from the participating classes. Such as you can see, we have three classes here: C1, C2, and C3. So discriminant functions correctly classify the classes of the example attributes, and if the function is not able to correctly classify one example, these examples are rejected. So again, you choose the class with the maximum probability. So you calculate the probability of the model or the example with respect to each class. And there can be k decision regions depending upon number of the labels. So we will discuss more about these kind of functions when we move our discussion towards certain topics which involve discriminant functions. So if we have two classes, we can classify the discriminant as a dichotomizer, that means division into two, or polychotomizer, that means division into more than two classes. So we calculate the probabilities of each class. For example, if we have two classes, we calculate the probability of the first class and the second class and take the difference. So if the difference is positive, we say that it belongs from class 1, otherwise it will belong from the class 2. There are several ways to predict the output class based on the probability theory. So before moving towards the Bayesian probabilistic networks, let's face a problem of probabilities using the association rule mining. So it is dependent upon the association between the input attributes or input transactions in this case, and to extract the rule to predict the most suitable classes. So as in this case, we have set up transactions where we have a general store and people buy different kind of products together. The objective here is to um, uh, find out the set of transactions from the given dataset and generate all the association rules that have support and confidence greater than the user specified minimum support and minimum confidence. That means find out the transaction which says that the user are more likely to buy particular product. So we have extracted a rule here that if people buy diaper, they are more likely to buy beer as well. Similarly, we have another rule which says people who buy beer and bread also buy the milk. So there are certain constraints on the association rule mining, which says that the items should be in the lexicographical order. That means the items must be ordered. So this is one of the applications which is implemented in real world, and the big companies such as Teradata does this association rule mining for more than 20 large retail organizations in the USA, including the retail stores, Walmart, and it is used for the pattern discoveries in the biological databases. So the association rule says that if people buy the product X, they are more likely to buy the product Y. So we have to check these associations to 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 ascertain that the user has the confidence to buy those products. So we can say that to find out the association between the probability of X and Y, we can say the customers who have bought both the products over the total customers. So if we want to check the probability of the customers who buy both the product and the customers who have bought a particular product, so we can check the association rule mining by probability of X and Y over the probability of the X. So in this case, we will have the customers who have bought both the products with the customers who have bought the first product. So here is the problem decomposition and implementation of a priori algorithm. And again, we have the set of transactions, and there's 4 of them, and we have calculated the support for each kind of item and the combination of items in the 4th example. So shoes are the most bought items along with the shirts and jackets at 50%, and the combination of shoes and jacket is again 50% because 2 transactions from 4 contain both of the products. So you can specify the support and the confidence criteria to calculate the support for product A and B over the total purchases, and the confidence that people buying A will also buy the product B. So you can go through this example to find out the association rules. So again, the a priori algorithm is applied here to find out the uh, confidence and support. So as you can see, we have another data space and we have simple transactions which have set of items bought together. So you scan the data set and get the most purchased item, and you can see that the item number 2, 3 and 5 are more purchased along with one less for the item number 1. So you discard the item number 4. So again, this is your first classified or first association rule, and then you again itemize the sets that how these items are bought together. You generate another set and you ignore where items are bought collectively are less than the confidence. Again, find out the support for the collective items on 2 levels, and then find out the support for 3 collective items. And finally, you can see that the item number 2, 3, 5 are bought collectively, which have the support greater than 50%. So the application of these algorithms are mostly relevant to product ordering, so that these products are placed closely with each other. So if you go through the example described in the previous 2 or 3 slides, you will you will come to know that the probability of buying one product with the another changes with the association rule. For example, if you change the support and the confidence criteria, there are more chances that more association rules will be created, and you can extract the probabilities of most bought products or most collectively bought products with one another. So let's move our discussion towards the probabilistic models, and we move back to the Johnny, the famous person who likes the pies. So look at the example here. We have the classification that uh, Johnny likes few of the pies and he dislikes the rest of them. So we have the one rule here which specifies the thickness of the pies. So we can see that there are 6 pies that Johnny likes, and there are almost 8 pies that have the thick filling. So in the probability theory, we can estimate that what is the probability of filling being thick so that Johnny likes the pie, and then what will be the probability of Johnny liking the pie that is from the thick filling. So this leads us to some basic probabilities or basic definition of the probability. So we have three basic definitions: the relative frequency, the conditional probability, and the joint probability. The relative frequency is the occurrence of event or the occurrence of variable in an environment over the total occurrences of all the variables. For example, in the pies domain, we had the 12 example and we find out the relative frequency of the examples or variables acting as positive. So we can find out the probability of the positive over the total. So we can see that there is a 50% chance of of positive example, or in other words 0.5 probability of occurring examples as positive. So on this assumption, we can say that if we had 24 examples, the 12 examples will be positive. So conditional probability, on the other hand, is the probability of occurring a particular event with respect to occurrence of another similar event. That means it is the occurrence of two variables simultaneously. So for example, again we calculate the probability of positive clauses given that the um, the bar symbol is often pronounced as given that there is the thickness involved in the pies. In simple English, we will say that what is the probability of positive classes given that the positive classes have the thickness or the crust filling as thick. So that means we can find out the positive classes which has the filling of thick over the total thick pies. So this leads us to the 0.375 probability or 37.5% chance of the positive clauses being thick. Joint probability is occurrence of two events or two variables simultaneously. So this is expected as the probability of conditional or the conditional probability of both variables with the individual variables. So you multiply the conditional probability of both variables with the second variable for which you want to calculate the probability. For example, in this case, we want the probability of positive clause and the probability of thick clause occurring at the same time. In simple English, we want to calculate how many examples are positive and thick. So we had the conditional probability of positive and thickness is 3 by 8, and there are total 8 occurrences of relative frequency of thickness over the total example, which is equal to 8 by 12. So we have the resultant joint probability, which is 3 by 12. That means 3 examples occurring positive or thick. So based on this joint probability theory, we extract the Bayesian formula, which is based on, again, the probability theory. So we have defined the two terms, the joint probability and the conditional probability. It is worth to note here that the conditional probability should not be confused with the joint probability of two events occurring simultaneously. So use the right notation. For example, for the joint probability, we have used the comma symbol, and for the conditional probability, we have used the bar symbol. And further to that, joint probability is commutative as well. Therefore, if you have the joint probability of the class with the positive and crust with the thick, you can extract it using the conditional probability of occurring class as positive while it is thick with the conditional probability, and multiply by the prior probability of the uh, relative frequency of thickness. And it is commutative. Similarly, if you want to reverse the direction, or in other words, you want to calculate the probability of thickness while it is positive, you multiply with the probability of being positive. So from here you can extract the formula of Bayesian network. If you transfer this from left hand side to the right side, we extract the formula to extract to find out the probability of positive clause if the attribute has the thickness value, or based on the thickness. So we may find the probability or conditional probability of the class being having the value of pi in the thick and in the positive uh, domain, multiplied by the prior probability of class having the positive. So we extracted probability of being thick slash positive in the previous slides. In other words, how many examples are thick which are positive? So there were three cases of examples which were positive, and there were total 6 positives. So if you multiply by with the probability of positives, it is 6 by 12. And if you find out the probability of occurrence of thickness, it was about I think 8 out of 12. So you can calculate by solving these values uh, to find out the probability of positive attributes or positive target values while the thickness is available. So based on these assumptions, probability of pi with the thin filling being positive is calculated as this formula derived from the previous slide. On the other hand, probability of pi with the thick filling being negative is calculated in the similar way, but this time the conditional probability of the positive is changed with the negative. So you should choose the label with the higher probability. So any example you encounter in the Bayesian classification, you put these values to find out the prior probabilities of class being positive and class being negative. So you have to choose the value with the most or higher probability value. So the problem is not restrained here, just like the previous classification problems. Many realistic applications have more than two classes, not just the positive and negative class as we depicted in the pi domain. So again, if we have more than one label, the labels are listed as C of j. So which means C of j or C of I, any literal you can use. So if we use the C of j, then it is the label of the jth class, and if we use the attribute vector x describing the object we want to classify, the Bayes formula requires the resultant form. So just you will notice there is a slight change here, which shows that instead of a positive and negative probability, you have replaced those binary classification with the multi-class labels, and you calculate the probability of each class and compare with the new example, and you assign the new example with the highest probability uh, found out from the given formula. So another consideration here that this approach works with the mutually independent attributes. What is needed is a formula that combines the probability of individual attribute values into the probability of given attribute vector in the given class. So we have mutually independent attributes represented as the attribute vector x of I. Mutually independent attribute means all of the columns are independent and there is no dependency between the columns. So we can use the independency attribute to calculate all of the probabilities of individual attributes by multiplying with each other. So we use the naive Bayes symbol in this form. So the whole Bayes formula is converted by replacing this value at this location. So the resultant formula will be like this. But it is also essential to keep in mind that the assumption of mutually independent attributes is rarely justified. There are many applications where attributes are dependent on one another. For example, if you are calculating a person's physical features, so a person's weight grows with its size, or the quality of the healthcare may be traced by the individual's income, or the age is dependent on the date of the birth. There are so many physical properties that are derived from one another. So in short, domains where two attributes are not in any way related to each other are very rare. So no wonder that the above described approach is known as under the unflattering name naive Bayes, which means it is very novice and a beginner approach. So here is another illustration of the previous replacement of the formula, which shows the probability of individual events which are independent. So we have replaced the main Bayesian formula with the probability of each attribute and then combined the probability by multiplying with each other. So we have a given classifier and input feature vector which are independent. Therefore, we have the conditional probability of the feature vector dependent on individual features or feature values. So there is another one practical comment which we have been observing in previous few slides, it is about the denominator, which is constant in all of the divisions. So you can note that the probability of the events for particular attribute vector is the same for each class or each label. So if you have multiple labels, then you should choose the label with the highest numerator. That means you do not have to worry about the denominator. Choose the value with the highest numerator. So next task is to use these Bayesian concepts to apply probabilistic classification. So you can establish a probabilistic model for classification using the discriminative technique and generative technique. So in the discriminative technique, you use the discriminant function which discriminate different classifications or different classes based on the feature attributes. In the generative model, you use the prior probabilities of feature vectors to predict or to generate the output labels. So these are used interchangeably in the similar formula. So just you can see uh, we have the probability of class given the feature vector and the probability of the feature vector given the class, which was used interchangeably in the previous slides. To assign the probability or to assign the class, you use the map classification rule. MAP stands for maximum a posterior. That means maximum probability or maximum posterior probability. So you assign any new example, for example x, to a class referred as C steric. So if the probability of the class, if you assign it the C steric for that particular example, is greater than the all other labels. For example, if you take the example of the sports car, and you will only assign the new example to the sports car if the probability of the sports car for that particular example over the dataset is greater than the probability of rest of the cars. So here the C is not equal to C steric is the conditional probability rule. Or you can simply use the generative classification rule mentioned here or even in the previous slide just by taking the numerator and ignoring the denominator. So this slide will illustrate you to the actual working of naive Bayes algorithm. So the example is to be classified is described by the feature vector x, which consists of the list of attributes used to describe that particular example. So for each previous example referred as xfi and for each class label referred as cfg, you have to calculate the conditional probability. For example, you calculated the probability of being thick and class positive in the previous slide, which was referred as P of x of I given C of j. So you calculate the probability for both classes in that example, for example, positive class and the negative class, which are labeled as C of j. So as the relative frequency of x of I among these training examples that belong to the same label C of j. So after calculating these prior or relative frequencies and conditional probabilities, now for each class label carry out the following two steps. Now calculate the probability for each label. For example, probability of positive and negative as the relative frequency of this class in the training set. Next, calculate the conditional probability P of x given C of j using the naive assumption of mutually independent attributes by the given formula. So that means calculate the probability or mutually independent attributes by multiplying the probability of each attribute value with same class label. So once you have calculated all the probabilities, the next task is to choose the class with the highest value of this value. Remember, this was the numerator of the naive Bayes algorithm. So you can further understand the naive Bayes concept with one of the examples from the same domain we have been discussing, the Johnny liking the pie. So first step was to identify the example which you want to classify. So here is the example which is represented by a feature vector x, and we have 5 attributes. In the first we have the value of square, thick, gray, thin and white. So recall that our pi domain had the 5 attributes. So the first step was to calculate probability of attribute with the class symbol. So put the first attribute and first label. So we have two labels here, so there will be 10 probability calculations. So we use the first label, first attribute with first label, second attribute with the first label, third, fourth and fifth attribute, and calculated their relative their conditional probability. And similarly for the negative we did the same. So if we had multiple classes, we would have done the same calculation for number of labels. So based on these values, we obtain following two probabilities using the naive Bayes algorithm. So we replace these values, or we put these values into the mutually independent attribute condition of naive Bayes, which calculates the probability of x being positive and x being negative. So mutually independent attributes are multiplied with each other, and the resultant probabilities are calculated. So since we can see that the probability of positive class is less than the probability of the negative class, therefore we label x with the negative class. So here is another example. So I will leave the discussion here and you can go through this example on your own. So you can see there are 4 attributes in this example and one target label. Again, the target label is binary, much similar to the previous example. Positive and negative is replaced as yes and no. So again, calculate the conditional probabilities of both uh, the labels with all the attributes. So you calculated for the outlook, temperature, humidity, and wind with the labels yes and no for each type, and you had the probability of the uh, positive class and the negative class. So after that you had the new instance and you calculated the conditional probabilities for those classes, and then we used a map rule to calculate the probabilities using the naive formula of the for the independent attributes. So as you can see, Again, the probability of positive class is less than the probability of negative class. The example will be labeled as negative class. Naive Bayes is a simple algorithm and it runs with many relevant issues. So first issue, as we highlighted previously, is the violation of independence assumption. That means there are too few real-world examples which have mutually independent attributes. However, naive Bayes works surprisingly well anyway without considering much about the variation or violation in the independence of attributes. So there are also some situations where you have zero conditional probability problem. For example, in the dataset you may have examples from only positive class and there are no examples from the negative class, and you may have the probability for that particular class equal to 0. Therefore, you will not be able to classify any examples into that particular class. So in these circumstances, conditional probabilities are estimated with an M estimate given by the following formula, which states that we calculate the probability using the M estimates for the class labels with the values of NC plus MP over N plus M, where NC is the number of training examples with which the data label is labeled as example and class labels as CFI, and N is the number of training examples for which the class label is equal to positive or negative. P is the prior estimate, which is usually provided before the calculation, that what is the probability of occurring both of the classes. So M is the weight which is controlled by the user, which is the number of virtual examples, and usually M is greater than 1. So we will discuss this technique in next few slides. Before moving forward, we have another issue, which is the continuous valued attribute problem. So there are many cases where the attributes are continuous or belong from the continuous domain, and these have the numberless values, for example textual values or continuous numeric values. So conditional probability can be modeled with the normal distribution using this formula, which calculates the mean and standard deviation from the continuous or normal distribution of the uh, input attribute. So for the probability of continuous valued attributes, there are several solutions, and one of them is using the probability density function, so which we will also discuss in next few slides. So there are three issues listed here, and the first is one of the most irrelevant, and it has limited impact on the working of naive Bayes. However, the second and the third problem impact the working of naive Bayes, and we have several techniques to encounter these issues. So the first, as mentioned, is the probability of rare events, are often referred as M estimate. So for example, we have a situation where we flip the coin and we have the two possible outcomes. A coin may result in the heads or tails. So to balance the probabilities, we have to uh, include our previous or N estimates. So we provide that for a fair coin, let there be number of heads out of number of all coin tosses. So it is conceivable that a coin flipped 4 times comes up heads 3 times. So for fair coin we have the probability of 50% of heads and 50% of tails, but if we toss it 4 times and we get 3 heads, we will get 75% probability for the heads. So the physics of the experiment suggests that a fair coin should come up 50% for the heads and 50% for the tails. So can this prior expectation, because this is our prior expectation that it will have 50% outcome for both of the results, can this help us to improve probability estimates in the domains with insufficient number of observations? That means we do not have the enough data to support our evidence because we tossed it only 4 times and our evidence says that we have the 75% probability. So the answer is again an estimate, and in this example we can calculate the prior probability of heads by counting the number of heads over the total and adding the prior estimate multiplied by a number m and again dividing by the same number. So here m is a parameter which is a user controlled parameter or a developer controlled parameter. So consider the 5 tosses of coin and you estimate the probability of heads based on the first n tosses. So in the first toss you had the heads as an outcome. The relative frequency of heads is equal to 1. So again you had the prior knowledge. You said that there is 50% of probability of getting head. So you calculated the m estimate and you had the frequency of 0.67. There is another head which also weakens the m estimate and it also rises, and once there is a tail the m estimate drops significantly closer to 0.5, and with another tail it crosses to 0.57. So the formula degrades to the prior expectation referred as pi of heads. So if we consider that there are all of the heads which are equal to 0, so we had the formula probability of heads is equal to number of heads divided by total number plus m estimate multiplied by probability of heads which was 0.5. So which is, if we had m is equal to 2, so we had led to 0.5 gain. Conversely, it converges to the relative frequency of if all of the tosses and all of the heads are so large as to render the term the m estimate and m negligible. Using the values of 0.5 as the prior estimate and m is equal to 2, we may get the probability as n of heads plus 1 divided by n of all plus 2. So the smaller the value of m, it is more difficult to convince the prior probabilities. And if you have the greater value of m, there is less chance that your prior expectation will change if your outcome is quite away from the different labels, which is depicted here. As you can see, if we had uh, the higher value of m, for example 100, the confidence is high. If there are more heads than the tails, there is a slight deviation in the probability of heads. However, on the other hand, if m is very small, the confidence is very low. For example, if we slightly change the value of n of heads, there is change in the probability of heads. So at the end, there was a final problem in the naive Bayes, and it was related to the continuous attributes. It is so difficult to calculate the probabilities of continuous attributes because there is so small deviation from one value to another. Therefore, there are two solutions to the continuous attribute problem. The first is the simple one, which says you can discretize and use the discrete valued Bayes formula. For example, if you have a series of values for a particular attribute, for example, if you can say you have the age length from 1 to 60, you can set this value to one of attribute, for example true, and any value which is not in the range to false. So this will help you to calculate the probabilities for these two sets. However, this will lead a lot of information loss and you may get problems predicting class labels. Another solution is to use continuous version of the Bayes formula, which is the calculation of class labels for continuous attributes. So in this way, you divide the continuous, continuous variables into small subsets. That means small intervals. So if the training set is large, then you can theoretically keep reducing the length of interval until they become very small. So the result of this small division will then no longer be a step function but rather a continuous function. So you can use this continuous function. In other words, you can employ a continuous probability density function to use or to calculate the probabilities of continuous variables. So now you can see you have replaced the value as p of x, the ci of x, which is the probability of continuous variable over the attributes. So these are the two examples that we discussed. In the first, you can discretize, and in the second, you can create a probability density function. So to handle the continuous attributes, you can employ probability density function, in short PDFs, instead of relative or conditional probabilities. So you can estimate these PDFs to find out the probabilities of particular attribute. So there are two approaches. The first is the usage of Gaussian Bell functions, and the second is also related to the Gaussian, which is uh, which is the superimposed usage of Gaussians. So Gaussian Bell functions show the probability density functions, and these are named after the great German mathematician. So the curve in the PDF is an example, and people call it a Bell function. So the maximum is reached at the mean point. That means this is the mean value of the attribute. For example, in this case, the age. For example, if we had the limit of 1 to 60 and the mean is 30 years, therefore we will have mean as a peaked value. And the curve slopes down gracefully with the growing distance from the mean with the standard deviation. So any point can be used as the standard deviation. So these represent the standard deviation from the mean to end points. So this is one standard deviation, this is two standard deviation, this is three standard deviation. So any point lying at this stage will be about two standard deviation away from the mean. So to estimate the Gaussian Bell function, you can use several formulas. So the Gaussian Bell function is defined by the first formula to estimate the probability of a continuous variable or a continuous attribute. So it says that probability of a continuous attribute x is equal to k dot e raised to power minus the value of attribute minus mean whole square over 2 standard deviation. So as you can see, the greater the difference from the mean of the bell curve, the greater the numerator, and thus the smaller the value of the probability of continuous attribute. So that means there is less probability that the item will be marked as this class, and the closer it will be to the mean, the larger the possibility, because the distance in the numerator will be less. So how can you calculate the mean, which is the simple mathematical calculation? You sum out all of the values and divide by the total number of values for that particular attribute. So for example, if we had 100 attribute values in a continuous variable, we sum those values and divide by 100 to find out the mean value in the PDF. So variance is calculated using the same formula, which is the square root of the standard, which is the square of the standard deviation. So again, you calculate the distance of each point from the mean and take it the whole square and divide with the total number of examples. So the steepness of the slope depends on the value of the variance. Greater the variance means smaller sensitivity to the difference between mean and the value x, and therefore flatter the curve will be. On the other hand, if the variance is smaller, the curve is narrower and towards the center. So the task for the attribute k here is to make the area under the curve equal to 1 as required by the theory of the probability that all the attribute occurrences must have the frequency equal to or probability equal to 1. So in simple words, Gaussian center mean is obtained as the arithmetic average of the values observed in the training example. On the other hand, the variance is obtained by the average of squared differences between any value and the mean. One another variation is you can notice that in the mean we divided by the total number of examples, and in the variance we divided by m minus 1. Here the intention of the writer is to compensate for the fact that mean itself is only an estimate. The variance should therefore be somewhat higher than what it would be if we divided by m. So of course this matters only if the training set is small. If we have large value of m, m minus 1 will not have the significant effect on the variance. While the Bell functions represent a good mechanism to approximate the probability density function in many realistic domains, it is not a cure to all problems. Some variables simply do not behave that way. Just consider the distribution of body to weight PDF in a group that mixes grade school students with their parents. So if we create the probability density function using the discretization method, we will observe two peaks. As you can see, we have observed two peaks. If we individually measure the PDFs for the height of the children and height of the parents, and if we measure the height of the another class of people, there will be different measurements of the PDF for each measurement. So once we combine, we may have different heads. So no doubt, if we combine, we may not represent the actual outcome or actual representation of the probability density function. A single band function would misrepresent the situation, but if we combine two or more of them, if we knew the diverse sources of these examples, we might create a separate Gaussian for each source and then superimpose the Bell function on each other. So there is a slight variation in the formula of the superimposed Gaussian. We have summation of all the calculations here. So in the formula, m is the number of examples. What if there are millions of them? It will be difficult to calculate. Again, normalization constant is used for superimposed Gaussians to make the area under the curve equal to 1. But if you have many examples, it will be very difficult to calculate the superimposed Gaussians for each of the examples. So for a training set of a realistic size, it is impractical to identify each training example with one Gaussian center. So nor is it necessary for all. So you have two solutions. You can choose a small random subset of examples to superimpose Gaussians for continuous attributes. Or you can use the clustering algorithms to identify typical groups of examples and then represent each group by its center of gravity, much like the discretization or the binning approach discussed previously. So after a hefty discussion about the naive Bayes, let's conclude the assumptions about the naive Bayes. So as described earlier, that naive Bayes algorithms are again based on the independence assumption that the attributes are mutually independent. And the naive Bayes is a very simple algorithm to classify the examples in a very easy and fast manner. It just requires considering each attribute in each class separately. Again, testing is also straightforward. Just looking up the table or calculating conditional probabilities with the normal distribution will give you the resultant class of the new examples. Naive-Bayes is a popular generative model and its performance is competitive to most of the state-art classifiers even in the presence of violating independence assumption. So this is one of the easiest and most widely used algorithm. It is based on the simple assumptions and performs quite well in many applications such as spam mail filtering. So apart from the classification, Naive-Bayes can do more in form of regression and other methods. Naive-Bayes is often used as a reference to which the performance of other approaches is compared. So that is the end of the lecture 2, and if you want to read more about the topic, you can go through chapter 2 of the reference book, or you can conduct a question and answer session. Thank you very much.